Okay, and so in the previous video we estimated both a European and American option. We verified the value here for European option, that's a call, and has these parameters for the spot price, exercise, risk rate, dividend, 2.0220, same as here. If we change to A, then we get the value for the American option, and it's a little bit more valuable. We can see that here because it's 2.05 in the algorithm that we ran in Excel VBA, and we're missing something, so value call. Okay, so we need another inverted commas. We just run that, and we should get this value 2.0508, 2.0508, and we're getting, again, the amount of time is negligible, but it's only 15 steps, which is consistent with what we have here in the 15-step tree, 15 steps, and again 15 steps in our tree. Okay, so what we noticed is that to bring this up to the same level of efficiency as Brody the Temple, we would need 15,000 steps, and again, that is, their paper was written in 1996, so computing power 20 years ago was a lot slower, so 15,000 steps was back then a relatively big estimation, but it was considered as a benchmark for being true, and we don't, in this compiler, we can't get up to 15,000. When we ran that experiment, we found that the exercise was killed. So it doesn't seem to work. Part of the problem here is that the structure of the tree, the way the tree is built in terms of setting out the binomial tree, each of the nodes here is defined, and we have a vector with an ij reference point, and this is constructed iteratively until the full tree over the 15,000 steps is built. That's an amazing number of nodes. That's close to 15,000 squared divided by 2. So it's the amount of memory being absorbed by setting out the tree in this particular fashion is huge, and that makes estimation difficult. So one of the solutions that we borrowed in particular from Espen Hogue was we took a dynamic type tree that was much more efficient in storing memory. But just maybe to set out before I get that far, just we might have a look at what that code actually translates into. So we might go back to our spreadsheet again, take another look, and bring over that same spreadsheet and look at that little snippet of code. Now there's a couple of snippets that I borrowed from develop the website, but if we take this snippet, I've just copied the Quinn-Q's adaptation of the binomial, and he uses this double loop, which is a way of generating the Sij binomial tree. And we could think of the loop as that for each j and for each I, we generate iteratively. We start with j, so j is our 0. Start at 0, we go up to as far as n, that's the number of steps. And we go j equal to 0, and then I has to go to 0 as far as 0, and then we go back through the loop, and of course we generate this price. The spot price is whatever the stock price initially was, times the power of u to j. If j is 0 and I is 0, then this is 1, and likewise power of 0 again, because I is 0. So in the first instance, we have the spot price. And then we develop from this loop, we have S0, 1, and then we adopt I goes up to 1. So I then goes from 0 to 1. And then we go through the loop again, and J is equal to 2. So these are the J's, and then I goes from 0 to J, and J is 2, so 0, 1, 2, and that keeps going until we get to the end. But every node depicted, so we can think of the structure of this tree as before, and this is how we generated it in our graph. But we can think of the stock price either going up or going down, and again multiplying by U squared, or multiplying by D, or multiplying by U, or multiplying by D, so SUD. U multiplied by D in the Cox-Ross-Rubinstein tree equals to the value of 1. So we recombine. So again, we saw that here also, and I didn't allude to it, but in this particular Cox-Ross-Rubinstein tree, we can see that the middle value here reverts to 100. Okay, so that's typical in Cox-Ross-Rubinstein. But the point I'm making in terms of this static type construction is that we have to record each of these values. In the static tree, this two-dimensional array is stored in memory, and then we have to call that back up when we run back through the estimation. So when we estimate the intrinsic value in the final node, when I is equal to n, when I goes from 0 to n, that's the final node, if you like, and n is, if n was equal to 4 here, 4. But each of these values have to are generated again, and we get the intrinsic value. And then as we go back through the tree, as we do the backward recursion, when we're estimating the American option, the Sij is pulled up from whatever was recorded here. So this vector, the vector double S that we've declared here, is an n by 1 by n by 1 vector. That's absorbing storage. We're also estimating the option, which is being also recorded, and the issue here is memory's being gobbled up, probably inefficiently. So a solution to that is I take VBA code from Hogue, and then I adopt that code into C++. So Espen Hogue, better find his book. So this is one of Espen Hogue's books. It's also where I found that VBA code for estimating a dynamic binomial model. I take that VBA code and I adopt it, and I develop a dynamic tree consistent with the structure outlined by Espen Hogue. But just the basic outline here would be, again, we create this stock price tree, but we don't start from here and develop each of the nodes from the starting point to maturity. We actually start here and estimate these values, and then go back, destroy these, bin them if you like, then create these. Once we run our option estimation, we perform additional backward induction. And as we move back to through the tree, we're binning the previous data points, which means we're freeing up a lot of data. Again, the structure of the IJ here is a bit different too, but we're destroying the data points as we run back. Now, if we look at, okay, so I basically have taken that code, the VBA code, and adopted it then to estimate C++. And so run the estimation again, but this is code that I taken from Espen Hogue. I made a few small changes. and we'll investigate those in a moment. But just to see the effect here of what those changes are. So initially, basically, we start off with, first of all, we have to check are the values correct. We can do that a couple of ways. One is we can look at the parameter values here and verify that they are the same as the values that we've seen previously in our Cox-Ross-Rubinstein tree here in this model for both the American and the European option. So we have a call for American, European, and using these parameters of SXT, the maturity 6 months, risk-free rate 7, B is equivalent to cost of carry, R negative Q is negative 0.01, which implies that the dividend is 0.8, volatility 20%, and 15 steps. We have 2.0508 as the value of the American option. Let's check that in the dynamic tree here, and this is the dynamic tree. So I run that again. This is the dynamic. Okay, so dynamic tree. And if I run our code here, it won't take long, using the same parameters as we just observed in the Excel, we find we're getting 2.0508 for the call, for the American call. Okay, so that's that value there. And for the put value, again, if we run for the European, we can check and just run, and it should be 2.02, which is slightly less, so 2.02201, which is the value that we have, 2.02201, which is basically the same value that we have here. So okay, we can see it's right. We can also adjust our results and I can paste these values in, 15,100. So these are values from Brody Temple 1996, 1996. Okay, so let's just take these values and just simply copy over, and I can do that just by removing nothing really changes here. I can just take these ones out and delete and paste. Okay, and we can remove the double forward slashes, and I'll do that. I'll pause and do that. Okay, so I've done that. So what I'll do now is I'll just run, but the values here are the values that we had taken from Brody and the Temple. Let's just take a look again at that paper. These values here. So risk-free rate 0.03, dividend, volatility 20%, dividend 7%, and the result we should get is 9.066. Now we got close to that with 5,000 steps anyway. This is still running, but just to verify it's the same numbers, and I might pause. Okay, yeah, we do get some output. Now, it took longer than 21 seconds, but we've got to acknowledge that data has to go up, the program has to go up to the server and come back, so I think there is some latency, but 21 seconds is what we estimate using this code here. And that value, of course, is the same as the value that we obtained in the paper, 9.066. But what's important is, of course, that the valuation was performed, whereas in the static tree, in this dynamic construction, using Espen-Haug style code, the estimation is run, and we get a number back, 9.0659, and that's a result that I verified before. So I'll just put that in as the correct result here. And okay, I'll pause here.